Today we are going to study chapter 12, final revision. This revision will be split into two parts, revision for geology, and this revision is based on chapter 8 because we took before a revision for chapter 8. If we go to this, you will find that we studied few chapters for geology and we took a revision in chapter 8. So this revision we are going to repeat it now, but of course quickly, so that this would be our revision for the chapters related to geology. Then we took few chapters related to soil mechanics. This we are going to study in chapter 12b next lecture, so that we would study the part related to soil, including the problems, and problems constitute a major part in the exam, so they are very important. Why we are studying geology? We are studying geology to know what all about soil beneath our structures, so that we can avoid problems that would happen in geotechnical engineering, because geotechnical engineering is based on geology. To understand, to be a very good geotechnical engineer, you have to understand geology. So we are studying geology to know the features of the earth below us, and to avoid it in our design of any geotechnical engineering problem. What is geology? The definition of geology, of course, it is very important. The geology is the science of earth. It gives you all the information about the earth. By the way, the age of the earth is about 4.5 billion years. So geologists concentrate on millions of years, but for us, we don't care a lot about the history of the earth. We only know it to know what we have reached now. We need the shape of earth now. What we know about the earth in the million years ago, or 4 million or 5 million years ago, is just something for info. It is not for us to study. We study the general shape of earth. This slide was very important because it shows you that geotechnical engineering is an engineering. It is not science, but geology and hydrology are sciences. What is the difference between science and engineering? Science is the study of everything around us, showing all the problems around us, but engineering, it takes the problem and propose solution for it. So we need to study geology, we need to study hydrology. These two sciences are very important. Once we study them, we can be a very good geotechnical engineer and propose solutions for any problem. Type of geologic data. The geologic data are split into 4 degrees of importance. The first one is information that is important for any human being. To know about earthquake, volcanoes, tsunamis, these are information that is required for anyone. So it is important for anyone on this earth. It is important especially for civil engineers who study climate, weathering of material, and so on. So civil engineers will have few topics that are related specially to them. Geotechnical engineers have very specific technical points that they need to study: faults, folds, dikes. These are important. As I just said before the lecture, you need to know what is the difference between dike and fault, so that when you solve your coursework, you do not use last year's coursework, because last year we were speaking about faults. This year we are speaking about dikes, so you cannot use the previous coursework as a new coursework. Yani it gives you some information, but it is not the full data. So this is important for geotechnical engineers. It is also important, of course, for geologists, but this is outside of our scope, because geologists study more specific in every branch of geology. This is outside of our scope. Why do engineers study? This is what we said. Why engineers? These are the valuable data that are related to engineers. Of course, engineers means civil engineers. So this is more data about this point. What was the geologic study plan? What did we study in this in the previous lectures? This is very important. The study itself is very important. Why? Because if I am studying something, I should have a plan. Why I am studying the Earth? This is the Earth now. This is the shape of the Earth now. To study this, to know the features of this shape, I need to know what happened to the Earth from the start till now to reach this. So the shaping of the Earth itself went through different stages. So there is something called geomorphic process. Geomorphic, geo is soil, morphic, or geo is earth, morphic is the morphology, it is the surface. So geomorphic mean the processes that shaped the surface of the earth. So how this happened, this is very important. How the shape of earth changed from being just one big continent, because as you remember in our previous lecture, we studied something called Pangaea. Pangaea is the name of the continent that gathered all the continents together as one shape. So this was the original shape. This is South Africa, this is, South America, this is Africa, this is North America, this is Asia and Europe, this is here Australia, and so on. All of these continents were just one piece, then they splitted. How they splitted, this is what we studied. Then geologic structures of the earth. When these geomorphic processes happened, of course, geomorphic processes are divided into, we are going to take this into two types. But so after the geomorphic processes happened, it resulted in geologic structures. So geologic processes is like the oven that heats your cake. If you have a cake, you put it in the oven and leave it for a while. In this time, it changes from one shape, maybe to a pastry, into a special shape. So now we need to study the geologic structure, as if you take the cake outside of the oven, cut it, to see what are the layers that are formed inside. So geologic structures are what resulted from these geologic processes, what happened after shaping the earth. Then there is something called geologic time scale. What is the geologic time scale? If this is my earth like this, my earth was at the beginning was small. Then it started to increase in shape. By increasing, it means that we are adding layers on top of this till we reach the final layer here. If I take a column like this, imagine that I dig a column like this, the upper layer will be the new layer. The lower layer will be the very old layer that happened with the creation of the earth. So the geologic time scale is as if I am imagining cutting into the earth, going kilometers inside. Each time I go below, I meet the layer that was formed very far away in time, and so on. Then we have the last thing called unconformity. This is the normal time scale. But suppose after I reach some geologic structures, I reach some layers, Earth was affected by some kind of erosion in some places. So in some places, as if somebody came and just removed this portion. It was removed away by any type of erosion. When it was removed, later new layers came here to replace what was removed. So in this case, I will have something called unconformity. Unconformity means the layers are not in the normal sequence. It was progressing in a special sequence, then suddenly, maybe this, as if you are going here, you reach this level. Then suddenly all of these layers were removed and new, very early layers came in place. So you are missing something in this geologic time scale. There is a portion in the time scale that is not available. In this case, I call this unconformity, and this we are going to study. By the way, this study plan is very, very important, because if you don't understand this, it means that you are just studying scattered information. I don't want you to study scattered information. I want you to know each chapter we are studying, why we are studying it, because we are building up information. We start with the geomorphic process that shapes the earth from the start till now. Then the result of this shaping is the geologic structures. Then I can have a time scale describing all of the layers from the early start till now. And in some cases, this time scale is not full. There are some missing gaps. These missing gaps are called unconformity. So these are our study plan, and it is important. We'll take one by one. Geomorphic process. This is the first one. As I said, geomorphic process is divided into two parts: endogenic process and exogenic process. As I said, geomorphic process is like the oven that cooks your cake. So how our earth was cooked to reach this shape? It was cooked by two forces. One of them is endogenic. It means that it is an internal process coming from the inside of the earth. Or exogenic, it is external process coming from outside, from the atmosphere or something like this. So this is the difference between endogenic and exogenic forces that shaped the earth. I will take the endogenic forces. The endogenic forces, it came from the inside. Coming from the inside, it is split into another two portions: fast process or slow process. Fast process, it means that the forces coming from the inside of the earth, coming outside, cooling. Of course, it is not forces, it is very hot material coming from the inside of the earth to build the earth, to add layers on top of the earth. How it comes? It comes through earthquakes, it comes through volcanoes, So all of these are constructive. Constructive means that it adds to the layer of the earth. But as I said in the previous lecture, how earthquakes are constructive, if I consider earthquake to be destructive, they are destructive for buildings, but they are not destructive for the earth. You may have an earthquake at one location, it may destroy all of the buildings, but though it destroys the building, it adds to the earth. The earth itself will increase in volume, increase in shape, so it means that the earth is constructive, but the buildings are destroyed. So this is the first process. Slow process means that the layers themselves, they can move vertically up and down, and this we can call isostatic equilibrium. This is very slow. For the layers to move from up to down, it is very, very slow process. Or plate tectonic. Plate tectonics mean that the plates move horizontally. The plates of the earth move right and left. So plate tectonics and isostatic equilibrium are very slow processes, but the fast processes are the earthquake and volcanoes. So slow process, fast process are part of the endogenic. Endogenic is the internal forces. Now we go to the this is a shape of them. This is how the below come outside. This is here the magma chamber. This is it contains magma inside. Magma is the molten rocks inside the earth. It just move horizontally at any or vertically at any location. It may go through a vertical pipe to be a volcano. It can move horizontally to give you layers and so on. So if it moves below the ground, then in this case it will be slow in cooling. If it go outside, it will be fast cooling and so on. So this is the difference between the fast cooling magma and the slow cooling magma. Now we go to the exogenic. We said that this was the endogenic. What about the exogenic? The exogenic means that something from the outside. What are this something from the outside? It is the weathering. You remember when we spoke about the earth, it was small like this, and we added layers on top of it till we reach the big shape of the earth. We said that sometimes at some special locations you may have this portion removed and then new layers would come, creating unconformity. How they are removed? They are removed by exogenic forces. So the endogenic forces build the earth, the exogenic forces removes the layers of the earth. So that's why we call it destructive. These exogenic are subdivided into weathering, mass wasting, and erosion. What about weathering? Weathering in Arabic, تآكل, something weathered. I put something in the air, I leave it for 1 month, I come after time, I find that it has weathered, it has disintegrated. Why? Because of the effect of the wind and the water vapor and everything in the earth. So weathering can be mechanical weathering or chemical weathering. Mechanical weathering means that pieces, the weathering happens due to movement, but chemical weathering just because of materials coming in contact with each other, reacting with each other, ending up having weathering this material. We will see mechanical weathering can be frost wedging, thermal expansion, unloading and exfoliation, or biological activities. We'll see this, and this is chemical weathering. Chemical weathering, if you look at the shape of the rock, you see that this rock is weathered, but pieces of the rock were removed, or sometimes pieces of the rock are removed and added at another location. Here, these three types, I think they are not included in this lecture. You have to check it in the original lectures. What is frost wedging? Frost wedging, if you remember that, we said that if we have two pieces of rock with a gap in between and water comes inside, when the temperature drops, you know that the size of water, of ice, is more than the size of water, so it will push the rock to the right and to the left. This will result in mechanical weathering because it is pushing the rock. If you refer to the lecture, you will find photos for this. Thermal expansion, if you have rock and this rock is affected by day and night, summer and winter, this variation of temperature result in removing some of the upper layers of this rock, so it is a type of weathering. Unloading and exfoliation, if you have a piece of rock below ground and then the ground was removed, so this rock is now in contact with the atmosphere, it will start, layers from top will be removed as if I am exfoliating it. Exfoliating means that in Arabic taqshir, I am just removing layers from the top. Biological activities, the roots of the plants, if I have a tree here and the roots go in between pieces of rock, when the roots increase inside, it pushes. And if you have any creatures living below ground, digging in this ground paths and holes, it is eroding this material. Chemical, as I said, it is just the action between different types of material. How to prevent weathering? This is a very important question. Whether it comes in an exam or it does not come in exam, but if you don't know this as an engineer, it is a pity. How to prevent as an engineer? How can I prevent weathering? I don't prevent weathering. Why? Because for rock to weather, it would take million years, 5,000 years. My building is not going to last more than 100 years. So why would I prevent weathering? If you find somebody telling you, did you take weathering into consideration in your design? It means that he does not understand geology. He just knows that there is something called weathering. But weathering takes a very long time. So I don't want to prevent weathering. I only take it into consideration that some weathering would happen during the lifetime of my building. My factor of safety will cover it. I don't need to prevent weathering. As a matter of fact, when to prevent a geologic feature, if it is within my capability. If I have a flood coming, I don't want to prevent the flood. I just want to know that there is a flood coming, so I will take my building away because I cannot stand in front of the flood. So if the geologic activity is very big, I'm not going to design anything. I will avoid it. Or if it takes a very slow time, I don't need to cover it. So in this case, are we going to prevent weathering? No, we are not going to prevent weathering. We just understand that there is weathering that may happen and it is a very long process. My factor of safety will cover it. The other type, as I said here, we have three types. Weathering, this is what we finished. Mass wasting and then erosion. What is mass wasting? Mass wasting is this. Mass wasting means that masses of the rock are wasted away. Pieces of the rock are falling away. I gathered all the type of mass wasting in these 5 categories. Something called falls, slide, topples or slump, flow or creep, spread. All of these are types of mass wasting. They can happen to land, to rock, to mud. So if you find mudslide or landslide, it is okay. Rock falls, it is okay. Rock topples, it is okay. Mud flow or mud creep or any rock spread. All of these, they do not depend on the material, they depend on what happened to the material. So what happened to the material in case of mass wasting? They either fall, slide, topple means just fall, crawling down. Flow means that it would move, but in case of if it is a little bit liquid, not liquid of course, but just like a paste flowing or creeping, then we have spread. It means that going away from each other, pieces going away from each other. So this can happen to anything, to land, to rock, to mud, so that you won't be confused when you hear something called rock fall and sometimes rock slide or rock topples. All of these are rock, but what is important is the description of what happens to this material. This is what we call mass wasting. How to prevent mass wasting? Do I need to prevent mass wasting? Yes, I need to prevent mass wasting, because as I just said, I may have something like this. This is a road here, and this is a piece of rock. And this piece of rock would fall. If it falls, it will fall in a second, and it would crash a car below, or somebody, or a house below. So mass wasting should be prevented. But erosion, we don't need to prevent it, but because mass wasting happens in a very short time. How to prevent it? There are many ways to prevent it. Reshaping of the slope. Put a slope that is not very steep, using retaining walls, using wire mesh shotcrete and rock balls, something just to fix the slope so that it would not fall. Using cultivated slope, just putting some kind of cultivation on the slope so that the roots would fix the topsoil and prevent it from falling down. So this is what is called mass wasting. The last thing is called erosion. What is erosion? Erosion can be subdivided into 3 parts. Wind erosion, or glacier erosion, or water erosion. Wind, of course you know what is wind. Glacier is the ice, the movement of the ice. Water erosion is the movement of water. You all know what is water erosion. When water is going in the river, it may erode the banks. So this is water erosion. Glacier erosion, when ice is melting, it moves. So the friction between the ice and the rock would make some kind of erosion. Then we have wind erosion. Wind erosion, when the wind passes by a land or on rock, it erodes the surface of the rock, of course after a very long time. But what is wind abrasion? There is wind erosion and wind abrasion. What is the difference between wind erosion and wind abrasion? Wind erosion means the wind itself erodes the material, but wind abrasion means the wind is coming, carrying sand inside it, and this sand, when it comes to the rock, abrades it. So in this case, abrasion means that the wind is not alone, it comes with the big brother. It comes with somebody else to help in the erosion. So in this case, it is called abrasion. So this is the difference between erosion and abrasion. How to prevent erosion? Not all types of erosion. If there is something called wind erosion, it is a very long term. I don't need to do this, especially that when I build on something, air is not going to reach this something. And it would take very long time, even if it is a cliff or something, it would take a very long time to happen. But in some cases, I need to prevent this erosion. Like if I am just I have, this is the seashore, and I want to make a levee. You know what is a levee in Arabic? Lisan. Yes, lisan. I want to make this levee in the water. If I leave it for 1 month, it will be eroded. So I have to put some kind of protection around it so that it would not be eroded. Or sometimes the seashore itself, like in Egypt here, we have, I think in Gamasa, in Baltim, there are places where the shore, it's even in Alexandria, the seashore of Alexandria, in some cases, the seashore is being eroded. So I need to put something. If you go to Alexandria, in some places, you find at the corniche that there is rocks that inside the sea. Why is this rocks there? To prevent the erosion. So it is just pieces of rocks added to prevent the sea or the water from eroding the soil, whether I made it or it is there from the beginning. This is the levee that I'm speaking about. This is man-made. They want to make a levee inside. So if they leave it as it is, it will be eroded in maybe 1 month. But if they put something like this, these pieces that connect together, they prevent water from just penetrating the soil with very high pressure, because they are going to hit these shapes, and the waves coming will be as if it is destroyed at the surface. So it ends up keeping everything in place. Now we go to the second thing. If you remember that we said that our geologic study is subdivided into many cases. Let's remember what were the geologic here. We said that geomorphic process, this is what we have covered now. Then number 2, geologic structures. What are geologic structures? Geologic structures is the final shape of the earth. The geologic structures are the final shape that the earth reached. These geologic structures are subdivided into 2 types. One of them is called primary or non-tectonic structures, and the second is called secondary or tectonic structures. Primary structures are the original structures that came at the beginning. Suppose that rock from below came on top of the earth, so it will form a layer. This layer, due to a volcano or something, it is, or even within the soil itself, it will stay there. But if later there is tectonic effects mean the earthquakes, shaking, going up, going down. So in this case, it is called tectonic structures. Tectonic structures include faults, folds, and fractures. So faults, folds, and structures are tectonic structures. Non-tectonic structures are the normal beds of the, if you go to a place, you have layers of soil, parallel layers of soil, then these layers are at the original shape that were shaped. Number 3, geological time scale. What is the geological time scale? I said that my Earth was small like this, then I started adding layers on top, layers, till I reached this big shape. So if I imagine that I took a column here, it will be something like this. This is the geologic column. By the way, when we go to the trip of the museum, I showed you there a column, and I told you that we took it in a lecture. This column, of course, it was a drawing for the column, because if somebody would tell me the height of this column, what it would be kilometers. It is not just a few centimeters or few meters. It is many kilometers below the ground. So each layer of this column, each layer represent an age, an era, or a time in the past. Of course, this was the oldest layers. Then something came on top, till we reached the early layers that were formed nowadays on the top. So these are what is a geologic time scale. It is this shape. This geologic time scale, geologists divided into Aeon, era, period, epoch. These are just definitions for time zones. Aeon is the biggest time zone. This Aeon is divided into eras. Eras are divided into periods. Periods are divided into epoch, and so on. It is not, you don't have to memorize it, but you have to know that there is something called Aeon, era, period, epoch. All of these are time scale. This is the biggest one, and this is the smallest one, just subdivision of it. How many million years? Lots of millions of years. Last thing, as I said, unconformity. This is your normal layers. Suppose that something happened, erosion happened here. At this layer, erosion happened. So all of this was removed. It was not there. Then later, starting from this, it started to come again. So in this case, this layer will be below here. It means that there is 2 or 3 layers that are missing. These missing layers are called unconformity. How this happens? Imagine that this is the shape of the layers. Of course, layers may be horizontal, may be curved due to movement of the earth. Anyway, imagine that to understand that they are just curved like this because of the effect of the horizontal forces. So suddenly, this upper layer was removed. So it ended up having the ground surface here, and as you can see, there is a dinosaur here. It means that this happened millions of years ago. Then other layers started to come on top. So here, this layer is a new layer. It was formed after the removal of the erosion of these layers. So these layers are missing, and in place I have new layers. These new layers may be horizontal, and these layers were not horizontal. So you will see an unconformity line. So if you have a site investigation and you have a borehole and you find this soil and this rock and this rock, and then other types of rock that belong to a very old ages, it means that there is an unconformity in this shape. This unconformity can be subdivided into 4 types. It is either disconformity. Disconformity means that there is a line of unconformity, but it is between 2 parallel layers of sedimentary rock. This is sedimentary and this is sedimentary, so this is called disconformity. Suppose the line exactly parallel. In this case, it is the same as this, but instead of having an irregular line like this, it is a parallel line, and it is called parallel unconformity. Parallel unconformity is very difficult to find, because you will find that there is no irregular lines showing you this, but geologists can say where it is found. The third type is called non-conformity. Non-conformity means the below layers are non-sedimentary. In the previous two layers, it was sedimentary on top of sedimentary. Here, it is non-sedimentary on top of sedimentary. It means that this may be igneous or metamorphic. So in this case, the line will be called non-conformity. The last type is called angular unconformity. This happens in case we have the below layers are angular, they are not horizontal, they are inclined layers. So these inclined layers are having an upper unconformity line. We call it angular unconformity. Now we go to, we will refer to this when we come to study the shapes of places where we have these features, so that we can know it. We will see it later. It's very important. Here, it is just exactly, I will take this very quickly because it is exactly what we said, but it is in terms of photos. What is our study plan? The four things: geomorphic process, geologic structures, geologic time scale, unconformity. This is very important, but it is just a summary of it. This summary is put here, and we have geomorphic process is subdivided in endogenic forces, and one of the endogenic is earthquakes. What are earthquakes? Because we studied a chapter called earthquake. What is earthquake? Earthquake is the movement of the layers at a depth below the ground, result in energy release. This energy would shake the ground, as you can see here. This is the focus where the release of energy started. This is the epicenter, which means that it is the center but on top of the ground, the projection of the center on top of the ground. Again, this is the focus, the epicenter, as I said. This is the types of the waves that propagate with the earthquake. We said that we have a P wave and S wave. These are the very important things for us, P wave and S wave. Why they are important? We said that they are important because they help us to locate the location, to fix the location of an earthquake, because P wave and S wave have different features. P wave can penetrate within liquid, because this portion of the inside of the earth is liquid. So P wave as a pressure wave can penetrate within the liquid, but the S wave cannot penetrate. So depending on where are you standing on top of the earth, you will record. If you have an earthquake here, you will record here the P wave and the S wave. Here you are going to record the P wave only. Here you are not going to record anything, neither the P nor the S wave, because the S wave was prevented and the P wave was deviated a little bit. So here is an area where we cannot find any wave. So depending on what you find, you will be able to fix the location of the earthquake. We said that if this is the location of the earthquake, I can just measure it at a point A and then measure it at another point B, and based on but I need to measure it in a place where I have the P and S wave. When I have the P and S wave, it means that I am near to the earthquake. Then I'm going to measure it at one location, I'm going to measure it at another further location, and based on the time lag between the P wave and the S wave, a difference in time lag, I can know the distance to the earth, to the location of the earthquake. If I measure it at 3 different locations, each location will give me a circle, means that the earthquake can be at any place around this circle. But if I have 3 locations, it means the intersection of the 3 circles will be in just one point. This point will be the epicenter of the earthquake. So I know the epicenter, but I don't know the focus. I don't know how below the ground, but I know horizontally where is the location. We said that we have 2 ways to measure an earthquake. It is a Richter scale or a Mercalli scale. A Richter scale, there is difference between the Richter and the Mercalli scale. You have, I will just won't repeat it again, but the main difference between the Richter scale and the Mercalli scale is that the Richter scale is the same everywhere. If an earthquake happened, if it is measured at any location, it will have the same value. But if it is measured by Mercalli, it will depend on where it is measured. So the Mercalli scale just does not measure the earthquake itself, it measures the destruction of the earthquake, so it differs from one location to the other. Another important feature is called the seafloor spreading phenomena. The seafloor spreading means that the earth, how the earth is moving, how the earth is expanding. It is expanding because we have convection currents below. This convection current pushes the crust, the upper crust below the oceans where it is very thin, so that it would break down, and when it breaks, new layers would come on top and fill the gap, and this would move, colliding with other layers, forming volcanoes and mountains and volcanoes at these areas. So this figure shows you how mountains are formed, how volcanoes happen, how volcanoes may happen below the ground. That's why some people would say, is it possible to have fire below the sea? Yes, there is fire below the sea. Where is fire below the sea? It is found at this location where the inside of the earth would come, that is very hot, similar to the degree of the sun. It is very, very, very hot, and it would come below the sea and start to cool. By the way, this is mentioned in Quran, that there is fire below the sea. This is where the fire starts. It's not fire, it is very, very hot, similar to the fire on the surface of the sun, and so on. Earthquakes, where earthquakes happen? Earthquake happens at the edges, as we said in the main lecture for this, that the earth is subdivided into plates. At the intermediate of the plate, nothing happens. But at the edge of the plate, this is the African plate. This is the edge of the African plate, where it meets the South American plate and the North American plates. So at this location, you may have earthquakes. At this location, you may have earthquakes, and so on. Here is, by the way, here is Japan, here is Turkey. This is the locations where you have major earthquakes, and so on. When we came to earthquake, we said that we have many types of earthquake shocks. we have something called foreshocks that would happen at the start, then the main shock, the main high shock that would happen, the major earthquake, and it would be followed by some aftershock that is less than the main shock, but though it is less, it is important because it is still destructive. What is the effect of the earthquake? The effect of the earthquake, it is shaking of the ground, liquefaction of the soil, and to tsunami. This is the shaping of the ground. This is the liquefaction of the ground, as if the soil liquefies, turns to be like a liquid, like water. And if you are standing on water, you will find that you are going to fall. And this is what happens to the building in this case. Some buildings fall and some buildings do not fall. Why? Because the liquefaction was very effective here. It was not effective at this location, and so on. The third effect is the tsunami. The effect of the tsunami is a wave coming from the inside of the ocean. It propagates till it reaches the shallow shore, so it's still very high and it can destroy everything in front of it. Earthquake prediction. Can we predict an earthquake? No, we cannot predict an earthquake. So far, there is no engineering way to predict an earthquake. And a prediction would be just few seconds, few minutes before you measure an earthquake at one location, tell people at a very far away that there is an earthquake coming so that they would start evacuating their place. Here again, this is the weathering. I told you that this I described when water comes inside the gaps and solidifies, turns into ice, creating these gaps. As you can see, this is a very good example of frost wedging, mechanical wedging. This is the thermal expansion. This is how the effect of day and night and summer and winter, they would remove portions of the rock, unfolding and exfoliation, removing of the upper layer here. So this rock is exposed. When this rock is exposed, so it is unloaded and start to exfoliate. It means that بتتقشر, as in Arabic, portion of it are removed. Mechanical weathering, as I said, roots of plants or creatures digging into the ground. Chemical weathering means that the effect of material next to each other weathering. This weathering may be due to the effect of, mainly it is due to the effect of water going through some types of rocks, weathering it, having caves, sinkholes, and all of these features. Now we, just a moment. Now again, this is just a repetition of what we said. What are the geologic structures of the earth? Because as I said, it is just a repetition of what we said in the first part of the lecture, but in terms of photos. Geologic structure, this is the normal bedding, horizontal like this. Sometimes it is graded, it is horizontal, but inside the horizontal layer, it is subdivided into coarse at the bottom and fine at the top, and it is repeated each layer. Cross bedding means that layers are inclined like this, but though it is inclined, there is a group action for this incline to move horizontally, so they are crossing each other. Curved beds like this, this is how the layers are curved. Of course, a long time ago, they were horizontal, but because of the effect of horizontal force to the right and horizontal force to the left, so they bulged up like this, or sometimes they would bulge down like this. This is a dike. This is a dike. By the way, this shows you the difference between a dike and a fault. This is a dike, and this is a graben. Graben is a double fault. This is one fault, and this is another fault. So a fault means that the layers fall down from one side. If I have these are the original layers, then suddenly they fall to this depth. It means that this is a fault. But a dike is just a filling inside the upper layer, in a crack in the upper layer. Rock outcrop means that pieces of rock coming outside of the ground. Falls means just that the layers move up and down due to the effect of horizontal forces. The types of falls, they are either anticline or syncline. Anticline means they bulge up, syncline means they bulge down, and this is the difference between the two. And this is an exact simulation of a fault. This was the top layer. Now it came here, this here. Maybe now it is there, and so on. This is a photo for the fault. A fault like this. This is the upper layer. Here it came here. This is here upper layer. It came here, and so on. Again, the geologic time scale, we said what is the geologic time scale. Again, what is unconformity, but in terms of drawing, we said this. I was looking for this photo to show you. This is exactly what I wanted to show you in unconformity. These are all inclined layers. Then when at a certain time, all of what was on top, maybe there was layer like this on top, all of them were removed. So the layers on top were removed, all of these were removed, and I started to have other horizontal layers on top. So this line is called the line of unconformity. The same again happens here. The same, this is a line of unconformity. Because this helps you to know when you see something like this, it means that there are missing layers in between. These are the types of unconformity in a summary, photo summary. Examples of unconformity in real life, two examples, they are important, very much important. There's something in UK, it's called the Sicker Point. The Sicker Point is something like this. These are the upper layers, and these are the lower layers. So this is a simulation. Upper layers in this direction with a special shape, and lower layers like this. A more complicated shape is found in the United States. It is the Grand Canyon. It is very important. It can be considered the most important feature, geologic feature in the world, because it includes lots of features together with each other. You will find here a line of something called nonconformity. Why it is nonconformity? Because here you have igneous rock, and here you have sedimentary rock. So the line between igneous and sedimentary is called nonconformity. So this is one type. Then I have here something called angular unconformity. Why it is angular unconformity? Because here there are horizontal lines, and these are inclined layers. So the difference between inclined and horizontal is called angular unconformity. Here you have all of these are called disconformity. Disconformity means the line separating horizontal sedimentary from horizontal sedimentary. That's all. We said that we may have a special case called paraconformity. If this line, I can consider this to be paraconformity. Why? Because this line is more or less horizontal, or maybe this line is horizontal. So at this location, I have all the types of this unconformity. So this is, the Grand Canyon is a very, you can go and see these layers there. So it means that, and each layer refer to a special time in the past, and it is clear for people to go and investigate. That's why it is very, very important. This is a simulation for it. These are the types of the different unconformity layers. Then the final case in our lecture would be, why are we studying all of this? This ends up mainly our lecture. Our geologic lecture has finished. Our revision is finished. But why did we study all of this? We studied all of this because we want to know the top layer below the ground, how we can deal with it. This top layer may be maximum 100 meters. The most sophisticated structure would need us to investigate 100 meters. The maximum available boreholes that I myself has supervised was 100 meters below the nuclear power station in Dab'a. This was the maximum, but usually it is 20 meters, 30 meters, 40 meters. This is the maximum. So within here, I can just make few boreholes. It means that I'm going to drill below, get samples while I am drilling, so that I can investigate what is happening. So if I take these boreholes and maybe go to something like this, if I go to something like this, here I will just take this. If I take a borehole here, I will find that in this borehole I will find a layer here, another layer here, another layer here. By the way, this was the topic of your coursework. It does not mean that I have a horizontal layer, this horizontal layer. How can I prove this? I will going to take another borehole here, another borehole here, another borehole there, and so on. Lots of boreholes so that I can prove what is the shape. So using boreholes, I can know the geologic structures, and to know what is the meaning of the geologic structures, I had to study the processes shaping the earth, so that I can reach these geologic structures. How can I, as a geotechnical engineer, detect them? I detect them via site investigations and via boreholes. This I'm going to do. Lots of boreholes. Based on these boreholes and based on my study of geology, I will be able to draw the layers without the need to do millions of boreholes. I will just, few boreholes can give me with some information, with some geologic information, I can detect what is below the ground. This is what I was just saying before I go to this slide. If I take a borehole here and a borehole there, maybe I would miss what is in between. So if I take another borehole in between, I will show you what is inside. Or maybe I would use geophysical survey. Geophysical survey is like the sonar that passes on the surface of the earth. It passes some kind of radiation and then collects it again. Based on this radiation, it can be analyzed and we can understand what is in between boreholes. So this is what I can do with the site investigation. Take a borehole here and there. Of course, it would give me a wrong impression that I have horizontal layers. I don't have horizontal layers. I have curved layers. So if I take a borehole in between, it would be good. And so on in all of the geologic features that I have studied. Of course, when we go to complicated geologic feature, this is just a fold, but it is a normal fold. But suppose you have a fold like this, very, very complicated. In a case like this, you as a geotechnical engineer will need the help of a geologist to tell you exactly what is there. So if I have a site investigation like this, I will have few boreholes. These few boreholes may detect a location of a fault, of a fold, of anything, and based on this, I can go to this point how to make my site investigation accurate. Number one, I have to study geology. Number two, I have to use additional boreholes, but not extensive amount. Based on my study of geology, I will know the adequate amount of boreholes that I need for a site. By the way, in our code, they say that in any site, as a minimum, you can have one borehole for each 300 square meters, and they will tell you the depth to go. This is also very, very important, that you know what is the adequate number of boreholes and the depth based on our Egyptian code. I think it will be given in the next lecture, but if it is not given, then you have to study it, because it tells you what is the minimum that you can do in any site investigation. Then another thing is to use geophysical methods, because geophysical methods are addition to the site investigation. It cannot replace a site investigation. I have to put my boreholes at the beginning, add geophysical methods to confirm the in-between of the boreholes. Then another thing is to inspect the surface. Maybe if I go to the site, look, I may see something outcropping or something available that would give me more information. This ends up our lecture for the revision of this geology part. It was a little bit long, but it was very important. As I said, it is more or less a repetition of what happened in chapter 8. So now you have all what you need to know about geology. Then we still have the revision for the soil part next time, inshallah. Thank you.